Hello everyone. In this lesson we're going to look a little bit more at reactions and the changes that occur in reactions. Specifically, we're going to be interested in how the energy changes. So remember, reactions are actually transformations. The matter is going through a change. We're breaking old bonds, we're making new bonds, we're changing one substance into another substance. We get different compounds with different properties. But the energy is also going through changes, and that gets back to the bonds. Because remember, chemical potential energy is stored in bonds. The reason atoms formed bonds in the first place was they wanted to become more stable. And that means when they formed those bonds, they released a little bit of energy and became stable. If we're going to change them into something else, we have to break those bonds, which means we have to put energy into it. We're going to call that activation energy. We'll look at that in a little more detail in a second. Breaking bonds is going to require energy because we're making it unstable. Forming bonds, like I said, releases that energy because it does make it more stable. However, not all bonds are identical, so the stronger the bond, the more energy it takes to break it, but also the more energy is released when it forms. So breaking a double bond is harder than breaking a single bond. We're going to be looking at the transformation between chemical potential and thermal energy. Now, thermal energy is something we can feel, right? If something feels hot, that means we're gaining thermal energy from it. If something feels cold, that means we're losing thermal energy to it. But we cannot create or destroy energy. So if the amount of thermal energy is changing, that must also mean the amount of chemical potential energy is changing. So if we feel a reaction heating up, that means we're getting more thermal energy out of it. If we're getting thermal energy out, that means the potential energy, that chemical potential energy in those things must be going down. We're converting potential energy into thermal energy. The opposite is also true. If we feel a reaction getting cooler, like it's taking thermal energy from us and getting cold, that means the thermal energy is decreasing. That must mean that the potential energy is increasing. Now, I mentioned earlier activation energy. Activation energy is what's required to start a chemical reaction because we have to get those initial reactants unstable and break the old bonds so that they can form new bonds. The energy added to start that is called activation energy, and it increases the chemical potential energy of everything in the reaction and makes them more likely to change. It basically puts them in a transition state. So they were in one state, they have some amount of chemical potential energy, and we're going to add energy to them to put them into another state. And up here, they are much more likely to change because they have much higher potential energy. And then they're going to transition, and they could end here or they could end here depending on what happens in this reaction. So we're going to start with some potential energy of the reactants. We're going to add some energy to make them change, to get them to transition, and after they transition, they'll end with a different amount of energy over here. These are the products. And we're going to look at a couple different cases. We're going to look at what happens if they end with more potential energy, what happens if they end with less potential energy. And that's where we're getting into endothermic and exothermic reactions. Now, we've seen the term exothermic before. When we were looking at phase changes, we know in an exothermic phase change, the substance loses energy to its surroundings. So we have the substance, it goes through an exothermic phase change, which means heat comes out of it, and that means this thing gets colder and the surroundings get a little bit warmer, and so we might have a gas change to a liquid or a liquid change to a solid. Those are exothermic changes. The substance is losing energy. Well, in an exothermic reaction, we've got to be a little bit more explicit about it. Thermal energy exits the reaction, but remember, the law of conservation of energy says that energy can't be created or destroyed, which means if the amount of thermal energy present is going up, the amount of chemical potential energy must be going down. So what's really happening is chemical potential energy is being converted into thermal. Let's look at a chemical potential energy graph. This is chemical potential energy. This is time. So at the beginning, we have the total amount of chemical potential energy of all of our reactants, right? This is before the reaction occurs. So they could change, but right now they're fairly stable because they're not in their transition state. We want to make them change, so we're going to go ahead and bump up the energy. We can heat it, we can stir it, we can add a spark, we can pass electricity through it. Lots of different ways we can put energy in, but essentially right here we have the transition state. And so they're no longer the reactants. We've broken bonds, so they're not the substances that we put in there, but they haven't formed their new bonds yet. So after we get them in a transition state, now they're able to form those new bonds, and so over time, as the reaction progresses, we're going to get this change, and eventually we get out our products over here, and the amount of chemical potential energy, as you can see, is less. So we started with a little bit of chemical potential energy, and we ended with less chemical potential energy. So we started here, and we dropped down to here. So the chemical potential energy decreased. But this loss of chemical potential energy is equal to a gain in thermal energy, which means if we, on the same axis, if we take thermal energy, it's going to start somewhere down here, and then as the reaction occurs, we're going to get more and more and more thermal energy until the reaction stops, and then what we lost in chemical potential energy, we gained in thermal energy. Now, the little bit of energy that we had to put into it to start it at the beginning, this bump right here, that is our activation energy. So this is an exothermic reaction because the chemical potential energy was converted into thermal energy. So the thermal energy came out, it started as chemical potential, was transformed into thermal, and the thermal energy exited the reaction. So the amount of chemical potential energy decreased, the amount of thermal energy increased, the total amount of energy remained constant. Of course, I'm sure you're all thinking, okay, that means we can have endothermic reactions, and you're exactly right, we can have endothermic reactions. They're going to be the opposite. Thermal energy is absorbed into the reaction and converted to chemical potential energy. Now, if you think about what that means the amount of thermal energy is decreasing, and if the amount of thermal energy is decreasing, this reaction is going to feel cold, the amount of potential energy is going to increase. So the products are actually going to have more potential energy than the reactants. So this is sort of like pushing a boulder up a hill. We've got to add energy to the reaction and keep adding energy to the reaction to get it to work, but it will actually happen, and we'll do an endothermic chemical reaction in lab. So this one sort of looks the opposite. If we have our chemical potential energy over here, it's going to start with a fairly low amount of chemical potential energy. And again, we have to activate this reaction, so we're going to have to bump up a bunch of energy. So we start right here with our reactants, and they don't have very much chemical potential energy. Then we put in some energy to get them to their transition state, so they're not reactants, they're not products, they're somewhere in the middle, and then the reaction happens and it'll stabilize a little bit, and then it might peter out right there. So again, we have our products, but they have more chemical potential energy than the reactants we started with. They're a little bit less stable, which means we can probably do another chemical reaction and get some of this chemical potential energy back out. We still have our activation energy. We still had to put in energy to get this reaction to go, and that activation energy does peak above our product energy, right? It did become a little bit more stable after the transition state occurred, but we had to put energy into this, which means if we had thermal energy being graphed here, the amount of thermal energy is actually going down. So we probably put in a bunch of thermal energy to get it started, and then as the reaction occurred, that thermal energy dropped. So again, the loss in thermal energy is equal to the gain in chemical potential energy.